1.4.5. Simplify expressions with square roots. Remember that when a number, n, is multiplied by itself, we write n squared and read it n squared. The result is called the square of a number n. For example, 8 squared is read 8 squared and 64 is called the square of 8. Similarly, 121 is the square of 11, because 11 squared is 121. It will be helpful to learn to recognize the perfect square numbers. A. Square of a number. If n squared equals m, then m is the square of n. What about the squares of negative numbers? We know that when the signs of two numbers are the same, their product is positive. So the square of any negative number is also positive. Open parenthesis, negative 3, closed parenthesis, squared, equals 9. Open parenthesis, negative 8, closed parenthesis, squared, equals 64. Open parenthesis, negative 11, closed parenthesis, squared, equals 121. Open parenthesis, negative 15, closed parenthesis, squared, equals 225. Because 10 squared equals 100, we say 100 is the square of 10. We also say that 10 is a square root of 100. A number whose square is m is called a square root of a number m. B square root of a number. If n squared equals m, then n is a square root of m. Notice open parenthesis, negative 10, closed parenthesis, squared, equals 100. Also, so negative 10 is also a square root of 100. Therefore, both 10 and negative 10 are square roots of 100. So, every positive number has two square roots, one positive and one negative. The radical sign, square root of m, denotes the positive square root. The positive square root is called the principal square root. When we use the radical sign, that always means we want the principal square root. C. Square root notation. Square root of m is read the square root of m. Radical sign. M is the radicand. If m equals n squared, then the square root of m equals n, for n greater than or equal to 0. The square root of m, radical sign, m, is the positive number whose square is m. We know that every positive number has two square roots and the radical sign indicates the positive one. We write the square root of 100 equals 10. If we want to find the negative of the square root of a number, we place a negative in front of the radical sign. For example, the negative square root of 100 equals negative 10. We read the negative square root of 100 as the opposite of the principal square root of 10. Example 1.41. Simplify. A. The square root of 25. B. The square root of 121. C. The negative square root of 144. Solution. A. The square root of 25. Since 5 squared equals 25, the square root of 25 is 5. B. The square root of 121. Since 11 squared equals 121, the square root of 121 is 11. C. The negative square root of 144. The negative is in front of the radical sign. Negative 12. Try at 1.81. Simplify. A. The square root of 36. B. The square root of 169. C. The negative square root of 225. Try at 1.82. Simplify. A. The square root of 16. B. The square root of 196. C. The negative square root of 100. 1.4.6. Identify integers, rational numbers, irrational numbers, and real numbers. We have already described numbers as counting numbers, whole numbers, and integers. What is the difference between these types of numbers? Difference could be confused with subtraction. How about asking how we distinguish between these types of numbers? Counting numbers. 1, 2, 3, 4, dot, dot, dot. Whole numbers. 0, 1, 2, 3, 4, dot, dot, dot. Integers. Dot, dot, dot. -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. What type of numbers would we get if we started with all the integers and then included all the fractions? The numbers we would have form the set of rational numbers. A rational number is a number that can be written as a ratio of two integers. In general, any decimal that ends after a number of digits, such as 7.3 or -1.2684, is a rational number. We can use the reciprocal, or multiplicative inverse, of the place value of the last digit as the denominator when writing the decimal as a fraction. The decimal for 3 is the number 0.3 bars. The bar, over, the 3 indicates that the number 3 repeats infinitely. Continuously has an important meaning in calculus. The numbers under the bar is called the repeating block and it repeats continuously. Since all integers can be written as a fraction whose denominator is 1, the integers, and so also the counting and whole numbers, are rational numbers. Every rational number can be written both as a ratio of integers p over q, where p and q are integers and q not equals 0, and as a decimal that stops or repeats. A rational number. A rational number is a number of the form p over q, where p and q are integers and q not equals 0. Its decimal form stops or repeats. Are there any decimals that do not stop or repeat? Yes, the number pi, the Greek letter pi, pronounced pi, which is very important in describing circles, has a decimal form that does not stop or repeat. We use 3 dots to indicate the decimal does not stop or repeat. Pi equals 3.141592654, dot, dot, dot. The square root of a number that is not a perfect square is a decimal that does not stop or repeat. A number whose decimal form does not stop or repeat cannot be written as a fraction of integers. We call this an irrational number. B. Irrational number. An irrational number is a number that cannot be written as the ratio of two integers. Its decimal form does not stop and does not repeat. Let's summarize a method we can use to determine whether a number is rational or irrational. C. Rational or irrational. If the decimal form of a number 1. Repeats or stops, the number is a rational number. 2. Does not repeat and does not stop, the number is an irrational number. We have seen that all counting numbers are whole numbers, all whole numbers are integers, and all integers are rational numbers. The irrational numbers are numbers whose decimal form does not stop and does not repeat. When we put together the rational numbers and the irrational numbers, we get the set of real numbers. D. Real number. A real number is a number that is either rational or irrational. Later in this course we will introduce numbers beyond the real numbers. Figure 1.7 illustrates how the number sets we've used so far fit together. Real numbers. 1. Irrational numbers. 2. Rational numbers. 2.1. Integers. Dot, 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 -2, -1, 0, 1, 2, dot, dot, dot. 2.2. Whole numbers. 0, 1, 2, 3, dot, dot, dot. 2.3. Counting numbers. 1, 2, 3, dot, dot, dot. Figure 1.7. This chart shows the number sets that make up the set of real numbers. Does the term real numbers seem strange to you? Are there any numbers that are not real, and, if so, what could they be? Can we simplify square root of -25? Is there a number whose square is -25? open parenthesis, closed parenthesis squared, equals, -25, question mark. None of the numbers that we have dealt with so far has a square that is -25. Why? Any positive number squared is positive. Any negative number squared is positive. So we say there is no real number equal to square root of -25. The square root of a negative number is not a real number. Example 1.42. Given the numbers -7, 14, over 5, 8, square root of 5, 5.9, negative square root of 64, list the A. Whole numbers. B. Integers. C. Rational numbers. D. Irrational numbers. E. Real numbers. Solution. A. Remember, the whole numbers are 0, 1, 2, 3, ... So 8 is the only whole number given. B. The integers are the whole numbers and their opposites, which includes 0. So the whole number 8 is an integer, and -7 is the opposite of a whole number, so it is an integer, too. Also, notice that 64 is the square of 8, so negative square root of 64 equals -8. So the integers are -7, 8, and negative square root of 64. C. Since all integers are rational, then -7, 8, and negative square root of 64 are rational. Rational numbers also include fractions and decimals that repeat or stop, so 14, over 5, and 5.9 are rational. So the list of rational numbers is -7, 14, over 5, 8, 5.9, and negative square root of 64. D. Remember that 5 is not a perfect square, so square root of 5 is irrational. E. All the numbers listed are real numbers. Try it 1.83. Given the numbers -3, negative square root of 2, 0.3 bars, 9, over 5, 4, square root of 49. List the A. Whole numbers. B. Integers. C. Rational numbers. D. Irrational numbers. E. Real numbers. Try it 1.84. Given numbers negative square root of 25, -3, over 8, -1, 6, square root of 121, 2.041975, ... List the A. Whole numbers. B. Integers. C. Rational numbers. D. Irrational numbers. E. Real numbers. 1.4.7. Locate fractions and decimals on the number line. We now want to include fractions and decimals on the number line. Let's start with fractions and locate. 1, over 5, -4, over 5, 3, 7, over 4, -9, over 2, -5, and 8, over 3, on the number line. We'll start with the whole numbers 3 and -5 because they are the easiest to plot. See figure 1.8. The proper fractions listed are 1, over 5 and -4, over 5. We know the proper fraction 1, over 5 has value less than 1 and so would be located between 0 and 1. The denominator is 5, so we divide the unit from 0 to 1 into 5 equal parts: 1, over 5, 2, over 5, 3, over 5, 4, over 5. We plot 1, over 5. Similarly, -4, over 5 is between 0 and -1. After dividing the unit into 5 equal parts, we plot -4, over 5. Finally, look at the improper fractions 7, over 4, 9, over 2, 8, over 3. Locating these points may be easier if you change each of them to a mixed number. 7, over 4 equals 1 and 3 over 4. -9 over 2 equals -4 and 1 over 2. 8 over 3 equals 2 and 2 over 3. Figure 1.8 shows the number line with all the points plotted. Figure 1.8. Example 1.43. Locate and label the following on a number line. 4, 3, over, 4, -1, over, 4, -3, 6, over, 5, -5, over, 2, and 7, over, 3. Solution. Locate and plot the integers, 4, -3. Locate the proper fraction 3, over, 4 first. The fraction 3, over, 4 is between 0 and 1. Divide the distance between 0 and 1 into 4 equal parts, then we plot 3, over, 4. Similarly plot -1, over, 4. Now locate the improper fractions 6, over, 5, -5, over, 2, and 7, over, 3. It is easier to plot them if we convert them to mixed numbers and then plot them as described above. 6, over, 5, equals, 1, and, 1, over, 5. -5, over, 2, equals, -2, and, 1, over, 2. 7, over, 3, equals, 3, and, 1, over, 3. Try at 1.85. Locate and label the following on a number line. -1, 1, over, 3, 6, over, 5, -7, over, 4, 9, over, 2, 5, -8, over, 3. Try at 1.86. Locate and label the following on a number line. -2, 2, over, 3, 7, over, 5, -7, over, 4, 7, over, 2, 3, -7, over, 3. Since decimals are forms of fractions, locating decimals on the number line is similar to locating fractions on the number line. Example 1.44. Locate on the number line. A. 0.4. B. -0.74. Solution. A. The decimal number 0.4 is equivalent to 4, over, 10, a proper fraction, so 0.4 is located between 0 and 1. On a number line, divide the interval between 0 and 1 into 10 equal parts. Now label the parts 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1.0. We write 0 as 0.0 and 1 as 1.0, so that the numbers are consistently in tenths. Finally, mark 0.4 on the number line. B. The decimal -0.74 is equivalent to -74, over, 100, so it is located between 0 and -1. On a number line, mark off and label the hundredths in the interval between 0 and -1. Try at 1.87. Locate on the number line. A. 0.6. B. -0.25. Try at 1.88. Locate on the number line. A. 0.9. B. -0.75. 1.4.8. Media. Access this online resource for additional instruction and practice with decimals. 1. Arithmetic Basics. Dividing Decimals. https://openstacks.org/l/25 dividedecim closing parenthesis.